For 112 and 113, we will be talking again about continuity and also how we can remove certain types of discontinuities. So as a refresher, let's talk about those three conditions that we need to have continuity at a single point. That was from our last lesson, and remember this is at one single point. So first thing, f of c had to be defined. So at any x equals c value, we can evaluate f of c. Then we have to have the limit of f of x as x approaches c exists. And this, of course, means that you have to have approaching from the left and from the right has to be the same. So we can find that limit. And the third thing is those first two have to be equal to each other. So that's how we use that notation there, saying that the limit is equal to the function value. That's how we would have something that is continuous. When we talk about in 112, the continuity over an entire interval, this means all three of these conditions have to be met at every single point. All right, so we aren't going to be able to prove these three things for every single point on a graph, of course, but we can use our really intelligent brains to figure out where the discontinuity might be and see if we can make it continuous at that point. So it sounds a little daunting, but it isn't too bad once we start looking at what we're doing. And then once we know that there is a discontinuity, we're going to, in 113, talk about how can we remove those. Some are removable, some are not. Of course, you know the removable ones are those we call holes, not asymptotes or essentials or the jumps. We can't remove those. So here's the formal definition of continuity on closed intervals. So if we're talking about a closed interval, meaning not the entire real number system, but we're only talking about from A to B here, like on this little graph, then we have to use only the one-sided limits, because obviously the function to the left of A doesn't exist, or to the right of B, so we only use the one-sided limits coming at A from the right and coming at B from the left. So that's the only change in the definition of continuity when we're talking about an interval. We may have to use a one-sided limit. Okay? So here, I already have some stuff filled in just to make this video a little shorter than the last couple. For what value of the constant c is the function f of x continuous on the entire real number line? So I have missing values in here. I have c there and c there. I'm trying to figure out what that c value is to make this a continuous piecewise function. So because it's piecewise, my concern is what's happening here when the x value is 2. Okay, so I'm going to use the definition of continuity, those three things, and a value of 2 to determine where that's going to happen. So first thing, I evaluate f of 2 using my function. So I plug that in and I get 2 cubed minus 2 times x, so I get 8 minus 2c. I'm looking for what c is, so it's totally fine that it's there. Then I have to look at the limit from the left and from the right. So from the left, I plug in my 2 to the top branch, and from the right, I plug it in to the bottom branch, and I get 4c plus 4 for the top, and 8 minus 2c from the bottom. Then, if this is going to be continuous, my two limits from the left and from the right have to equal each other, and they have to equal f of 2. But because f of 2 is one of those little, the right-handed limit, then I can just set them equal to each other like I did in this step and solve for c. So then it becomes some pretty basic algebra that you can solve and figure out what that c value is. So most of the time with a piecewise function that you're trying to make continuous, you just plug in these kind of domain restriction values to see what that value is that will make it continuous. Okay, here's one that's a little bit more challenging. It looks like I got cut off a little bit. There we go. So the first thing we have to do, again, now notice we have a 2. This thing might split at 2 and it might split at 3. So we have to find two different values probably. So the very first thing I do is I'm plugging in 2 to the top branch and the bottom branch, or middle branch. So when I plug in 2 to the top one, I thought of that as just x plus 2. So I factored the numerator, factored that guy, and canceled the x minus 2 with the x minus 2. So I'm using the top branch as x plus 2 because they're the same everywhere except at 2. Okay? And then in the bottom, or the middle one, I plug in 2 again for x, and I get an equation there. Okay? That was this first thing over here written in pink. The 4 is from the top. The 4a minus 2b plus 3 is from the middle. Then I just combined some like terms. So I brought that 3 over, and then this is one of the equations I'm going to have to use. Now there's 2 unknowns. There's an a and a b. So I will have to have a second equation. That's where our 3 comes into play. So I also have a break possible where x is equal to 3. So I'm going to plug 3 into the first and 3 into the second, and I get this equation over here. Sorry, right there. Okay, and then I have a system of equations, and I make it all work out. So I multiply, so I can eliminate the b's. So I multiplied by x equals negative 2, a negative 2, and then got b to cancel. So then I can solve for a. A is 1/2. Once I know a in a system of equations, I can plug it back in like I did right there and figure out what b is. So in this case, a is 1/2 and also b. Fun, huh? This type of problem is very, very common on an AP test. They like to ask these types of things. Okay? And then here is just how do we remove a discontinuity. Really, it's factoring. So when you factor, you can remove discontinuities. So the type of discontinuity is what I found out first. I factored both numerators to see if there was anything that canceled. If it cancels, then it's removable. If it doesn't cancel, then it's probably a vertical asymptote or an essential discontinuity. Asymptotes are essential discontinuities. The jump discontinuities only happen when we have piecewise functions or sometimes a step function, but we don't deal with those in calculus much at all. The piecewise functions are the only time you're going to get a jump discontinuity. So you can see here, I factored, I canceled, and then I finally said that f of x on the left had a removable discontinuity at a equals 1, and then whatever was left after canceling and removing, that was the g. That is the same as f everywhere except at a. And same thing with the one on the right, just some factoring and some canceling. Okay, I hope that's helpful, and good luck.